Hello and welcome to another Physics 11 lesson on fundamental forces and a little bit more extra on gravity. I tried to record this lesson a little bit earlier with some students' help, but unfortunately that video didn't have any sound. So what I'm going to do is I'm going to use the notes that we took during that session, and I'm just going to talk about them a little bit more and go over them with some audio. So for starters, what is a force? Anything that is a push or a pull is a force. And we can think about all sorts of things that are pushes and pulls, from you physically pushing on something with your hand to physically grabbing something and pulling it with your hand. Cars and trucks apply pushes and pulls all of the time. Two objects colliding also impact forces on each other as well. All of these things are considered pushes and pulls. So a bunch of different things can happen if you apply a force to an object. If you imagine pushing against a book on a table and it starts from rest and starts to move, if it started from rest and then ends up moving, it must have changed the velocity, so it must have been accelerated, so you can accelerate things. You can imagine if you're running as fast as you can and you run into something like a brick wall and come to a rest, you've stopped, so you were moving and then you've stopped moving, so you've decelerated. You could also imagine just walking up to that exact same brick wall that you ran into, and you put a hand on it again, and then you push on that wall. There's no way that wall is going to move, even though you're pushing on it, so absolutely nothing could happen. Or you could change direction. You can imagine throwing a bouncy ball at a wall, and that bouncy ball is going to hit the wall and then come back the other direction, so it's changed direction, and that wall pushed that ball to change its direction. And so you can think of lots of types of forces. In physics, we talk about four fundamental forces. So there are four forces that pretty much govern every single force in the universe. And every single push, every single pull you can think of fits in one of these four categories. The first one kids usually get right away is gravity. Any object with a mass attracts all other objects with mass. So every single one. In this one, we talk about frequent conversations around the Earth and the Sun, or the Moon around the Earth, or even people getting stuck to planets. We can't get off this planet. Well, it's hard to get off this planet because gravity pulls us down. But gravity also does interesting things like keeps our atmosphere on the planet. Our atmosphere has a mass, so it's attracted to our planet, and our planet is attracted to our atmosphere, so it stays stuck there. Interestingly, along those lines, if you have a very small planet, something like the moon, eventually there isn't enough gravity to keep your atmosphere stuck to your planet and you end up losing it. Something that's kind of sidetracked and interesting. The other one that kids usually get pretty quickly is electromagnetic forces. So I think in Science 10 or 9, you guys play with magnets and charges. You can take a north pole and a south pole of a magnet and you can see that they attract. You can take a north pole and a north pole of a magnet and they repel. So like poles repel, opposite poles attract, and same with charges. Opposite charges attract and light charges repel. So gravity and electromagnetic forces are the ones that we kind of deal with day to day and are kind of your Science 9, Science 10 forces, because everything we experience on a day-to-day basis is one of those two forces. To get to the other two, what we're going to do is we're going to revisit our kind of Science 9, Science 10 learning, and we're going to take a look at our model of the atom. Return to Science 10, and what we have here is we've got our nucleus with all of our little protons and probably some neutrons in there as well, and then around the outside we've got this cloud of electrons. Notice how this is not drawn to scale. Our electrons kind of look bigger than our protons, which is not the case. So if we think about this, and if we're only using our force of gravity and our electromagnetic force, this model might have a couple of flaws. So we can look and we can see, okay, our electrons are going to be attracted to our nucleus, so they're going to stay in that cloud around there. And, we can talk about gravity. The masses are very, very small, so there won't be a large force of gravity. And that's okay too, because this is still consistent. Our electrons, sort of like clouds around the outside, would be attracted to this mass in the middle. And so this works unless you look and think about the nucleus and what's going on there. What we have in the nucleus is a bunch of positive charges. And we just talked about, due to electromagnetism, those like charges in the nucleus would all repel. So if there's just gravity and just electromagnetism, all of the atoms would literally blow up. There'd be nothing holding them together. And enter the strong nuclear force. So the strong nuclear force is the force, it's a very strong force, but it acts on a very small distance. And what it does is it binds all those protons in the nucleus. So it's responsible for keeping all those protons, which would want to go ripping apart, together in the nucleus. The weak nuclear force, which we can see squeaking up onto our screen here, is a bit of a tricky one because we don't experience it a whole lot, and there isn't a really good example to talk about it. But what can happen occasionally is larger particles will spontaneously break down into smaller particles. A primary example of this is called beta decay. And what you have is you have a neutron, which we know lives in the nucleus of an atom and has no charge. And occasionally a neutron will break down into a proton, an electron, and a little thing called an electron neutrino. And the weak nuclear force is what causes this to happen. And that's kind of all I really want you to know about the weak nuclear force, is that it just causes neutrons to break apart. You could either say it causes beta decay or causes neutrons to fall apart occasionally. And that's the weak nuclear force. In classical mechanics, it isn't always convenient to look at those four forces. They are the four fundamental forces, and all forces will fit together in there. But let's look at some common forces that we will talk about this year in a bit greater depth. We'll talk about gravity, which we'll do a little bit more today, and we've already talked about a little bit, where anything with mass is attracted to everything else with mass. We'll talk about normal forces. So this is the force that stops solid objects from penetrating each other. So if, for example, I'm out on a rugby field and I'm playing rugby and I run into another rugby player, I went from potentially running very fast to an absolute standstill. So I experienced a force. But what I was the one that's moving, but we didn't actually go inside each other. So that resistive forces that stops me from penetrating a solid object is called a normal force. If I go slowly into water, that resistive force isn't there, so there is no normal force. If I go really fast, though, like if I jumped out of an airplane and then hit the water, then there would unfortunately be a pretty large normal force. Frictional forces. So frictional forces are forces that slow things down when they're sliding against each other or rolling, like on a bicycle. Tension forces are forces where we push or we pull with a rope or a string or sometimes a chain. So let's say you can't really push with a rope or a string, it doesn't work. Those are just pulling forces. Spring forces is a category of forces where things act like springs or are a spring. And most other forces that we can't think of to fit in one of those categories we call applied forces. So the trick here is to think about how all of these forces fit in those four categories, is with the exception of gravity, which is its own category, all of the other forces are all examples of electromagnetic forces. So that's worth thinking about for a little bit, because we're not normally used to thinking about these as electromagnetic forces. We're thinking about magnetic poles and north poles and south poles. We're thinking about building static charge up on objects, or we're thinking about individual like electrons and protons and how those are interacting. So how do I justify saying that something like pushing my friend is an electromagnetic force? So we have to think about what actually causes that interaction. So when I take my hand or two hands and I push it up against my friend's chest and I push, What is actually happening is all of the charged particles in my hand are what's interacting with all of the charged particles in my friend's chest. And so it's those positives and negatives interacting that cause that force. Which is just an interesting way to think about things. If we think about spring forces, if we think about grabbing two ends of a spring and stretching it apart, what we actually have is a bunch of connected electrons and protons, that's all electromagnetism, in the spring that want to pull it back to the shape that it was in. Same thing happens if we take that spring and we compress it. We have a bunch of charged particles that want to return to their original form because of electromagnetic forces, and they push it back out. So every single one of those forces is electromagnetic forces. So what we're going to do next is we're going to talk a little bit about gravity in particular, and then I will do some gravity examples, which I'll do in another video that are numeric. But for now, we're just kind of talking, and I've written some stuff down. Gravity is super interesting because we've known about it for a long, long time. Newton was the guy who originally did work on gravity, as some of you may know, and he didn't really know what it was. But what he did do was he knew how he figured out how to calculate how strong it was. So he could calculate the magnitude of the force between the sun and the earth, or the earth and the moon, or even a person in the earth. But he didn't really know what exactly it was. And we're going to replicate some of his work because it's super useful and still used today. So the current theory, thanks to Einstein and his general theory of relativity, was that gravity is the actual bending of space-time itself. And space-time is kind of like the fabric of the universe. So you've got your 3 dimensions of space, which you guys are used to seeing at this point, X and Y, and then to get 3 dimensions, we add Z, and so then you could locate anywhere in space with 3 dimensions. And then the 4th dimension is time itself. And this can be a little bit tricky to think about because we're thinking about 4 dimensions. But there's a couple of YouTube things that we can take a look at.
The explanation for gravity is that matter bends space. And so you put mass in a place in space, it warps space-time, and objects are not feeling a force of gravity, they're just following the natural curvature. And so this is a sheet of Lycra. Where do you get this? This is my old bike.
If I'm lucky, I've fixed it and the video is still going to work. So let's hit play.
Literally a spandex.com. You can get a sheet like this if you buy the sales.
And we can see he's taken a mass and he's put it on this space fabric.
Objects.
And you can see how objects with mass would
feel that curvature and move accordingly. And if you have more mass,
right there. On that.
If you have more mass, it's going to bend space-time more. And so if you have objects here, they are going to respond to that, right? And so you put something there, now it's attracted. Now, in reality, that big mass would feel the warping of space-time by the marble too, right? It would move a little bit, but we usually ignore that. You know, the Earth makes the sun.
That's a pretty cool demonstration a little bit ahead here.
But this one does lose energy and spirals in. Is when you study the solar system.
We're just going to watch this last one and then I'll move on.
Around the sun the same way. Why is that? Did God decide that he only liked clockwise, or depends on whether he's above or below the solar system, right? Why is everything going in the same direction? Well, the answer is it wasn't. Different directions. But there was a preferred direction. The disk it formed from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way.
It's a super cool demo of how solar systems and galaxies and things were formed and why everything travels in the same direction. Basically, anything that wasn't traveling in the preferred direction kind of got knocked out of orbit, which is cool. So the problem with this demonstration is it's only a two-dimensional plane. And what also happens with space-time is you can have something out of the plane, so you can imagine it going above that fabric and below that fabric this way instead of just this way. And it kind of starts to hurt your brain a bit. And that's still only 3 dimensions, but a little movie that might help, which hopefully is loaded. So this is a bit of an idea of what warping of 3-dimensional space looks like. We can see the X and the Y and the Z, and then it's bending all of those as an object travels through it. And that warps your brain a little bit. If you watch it, it kind of starts to hurt, and thinking about how planets, how the fabric of reality actually looks like this. And then we remember that it also bends time, so there's a 4th dimension as well, which is weird. And Einstein, of course, did all of his work trying to develop this theory well before he could do experiments on it. But I think within the last 4 years, it might have even been as short as 2 years ago, they've managed to do experiments where they would predict things from this called gravity waves, and they've actually found them. So there's support that this is, in fact, what the universe is like. And that's our current understanding of what gravity actually is. The math behind it, I'm not going to lie, is just straight up hard, and so we don't use the math there, but it's a good idea to have. So there's still ongoing research in this, and one of the things that physics in general is trying to do is trying to develop a single theory, a single mathematical model that describes why all of these forces happen. And modern research has gotten to the point where electromagnetism and the nuclear weak and the nuclear strong force are all understood within one singular model, but they can't take this model that has all 3 of those forces and figure out how gravity is connected to it as well. And so current research is trying to figure out how all 4 of these can be the same. And 2 things they're kind of looking at, one of which is quantum gravity, and the other is string theory, and they're trying to use both of these theories to figure out kind of the nature of the universe. So those are our 4 fundamental forces in the universe, and the next video will have a couple of numeric examples about gravity. Hope you're having a magnificent day.